This is a video of the update to the NeuroNavigator, particularly an update to the navigation panel itself with different controls and improvements in the way it looks, its aesthetics. The basic engine behind the NeuroNavigator, that is the SW Loretta, the physics and mathematics of the engine have not been changed, but the way to see the slices and the location of deviant z-scores and current densities, etc., has been improved. This is a free demo, actually, of a patient that was assaulted and struck in the right parietal region and has spatial neglect, that is, does not see anything in the left side of the world, does not shave the left side of his face, does not write on the left side of paper, and also has paresis or paralysis on the left side. As I move this cursor around, you can see the navigation tools are operating, and the actual value underneath the cursor is in the lower right corner here. This provides you with the telegraph coordinates. The frequency I set to 5 cycles per second, which is the greatest deviation from normal, is in the right angular gyrus, Brahman area 7, and the z-score value is 4.2116 underneath the cursor. So if I move it over here, now we're in Brahman area 6. Left precentral gyrus, or the right precentral gyrus, and the z-score value is 3.8. Those same values can be seen up here in the upper left. Now this panel, which can be retained, its settings can be retained, so if you close the navigator, relaunch it, you'll get this same view. You can change the view as you wish, and whatever view you've selected when you close it, that will be retained. Now there are 3 panels here. One is the settings panel that allows you to control the various displays, the slices in the upper right. This is under the object panel, the 3D model. I can turn the cortex on and off. There's the cortex. I can turn the head model on and off. I can move the head model around with the electrical scalp potential can be seen here. That is the value of the electrical potential, the z-score deviation from normal on the scalp. The scalp can be turned on and off down here, and I can make that more or less transparent. There's no transparency, now there is some. So this is the EEG, actually the deviation from normal in the right parietal on the scalp surface. But if I want to look inside the brain, then I make that transparent, or completely transparent, or I can make it disappear. The head model is up here. I can make that disappear or make it complete, no transparency in the head model. And I can also transverse through the head model. This is the cutting box is enabled. I'm going to select the axial slice, and then I'm going to go through the head. So you can see how you can navigate with the NeuroNavigator through the brain as you wish to identify regions of the brain that are most deviant from normal and linked to the patient's symptoms. Another part of the left panel here is the data type. We can look at the electrical potential in the scalp, or I can look at the Laplacian. And I can look at coherence, lag coherence, phase differences, or information flow. If I go back to objects and select connectivity, and I'm going to deselect the cortex and the head model, and I'm also going to go over to the right panel here under networks, and I'm going to select one of the networks, for example, an anxiety network. And I'm going to evaluate the connectivity of the anxiety network. I can move through the brain. I can make the scalp transparent and then navigate through the brain. I can add the cortex to give you a better view of what's going on. And then, of course, I can add the head and navigate through the brain, and I can also add coronal and sagittal slices, and navigate in a more constructive way, if you wish. That's through the anxiety network. Here's the dorsal attention network. And I'll show in a second how you can look at the Z-scores. But again, you can eliminate the cortex in the head, eliminate some of these other slices, and evaluate then the attention dorsal network. So this panel on the left allows you to look at these various aspects from current density to connectivity. And as I said, there's the data type with the electrical potential, but you can also look at lag coherence. You can look at phase differences. I'm going to come back up here and deselect the cortex in the head, so we just see the network. Go back to the data type and look at lag coherence. Now, these are Z-scores. There's nothing deviant from normal in lag coherence. So I can go to scale and change that scale so we can see more. That's of current density, but connectivity, we can see more or less of the networks when we do that. And so we have objects which control all the various views from the cortex in the head to the scalp to connectivity. We have on the left panel the data type. We also have the theme, so I can make this light or gray or whatever I want. If I want to affect the scales for the Z-scores or raw values, I can do that with the scalp. I can do it for the current density, which is the Z-scores we see here in the right parietal lobe. And min-max, there's various global and local changes. Navigation, I can jump to the absolute value, to the minimum or the maximum, or have a fixed point. So we go through frequency, including going to a movie. We can fix a point in the right parietal lobe, let's say, and we can run a movie just at that point. And every 500 milliseconds, then we start going through the movie at that particular point, which is Brabant area 40 right. And we're going from different frequencies. I'm going to stop it. We can hide these settings and just look at networks and the brain here. We got many different networks. We got executive network, language network, mood network, or depression network, pain, pleasure, salience, schizophrenia, tinnitus. The fusion tensor imaging, DTI, from the Gattani and Deschatten atlas of the diffusion tensor imaging. Here are the Hagman hubs. We can take a look at Brabant area or Hagman 1. And if we do this, we can look at which Brabant areas is it constituted by. Then we can sort by the maximum, minimum of the Brabant areas. You can see these Z-scores are all within normal range. This is the executive function. And we can look at those Brabant areas and sort to the minimum or max, etc. So you can look at all the Z-scores for each of the Brabant areas. There's Mesulam's neurological evaluations. There's the interconnectivity networks from 30,000 PET scans. That's Laird et al. So these networks are derived by PET scans and functional MRI and penetrating head wounds and strokes and tumors in classical neurology. We can also just go to the full screen and look at the axial view or the coronal view or the sagittal view or the volume view. We could just, this is the same as the Key Institute now. except this is a real MRI rather than an averaged MRI. You can see this is frequency 13 and the different Brodmann areas. We can look at the foreview as we were, and then the slice view. Go back to the foreview, and we exit the full screen. And we go back to 5 Hertz, where you see the deviant right parietal lobe. We can show the settings again, and this controls the speed of the mouse here under navigation. And then, of course, under objects, we can, again, navigate, eliminate the cortex as we wish, and add the connectivity, and view these areas as we wish. In this case, the scalp is no longer transparent. So both the currents and the connectivity can be evaluated with these navigation tools. One can export a file and save this session and then re-import it at a different time. You can export to the .swl, which is a tab delimited file, or the connectivity. These are tab delimited files. You can also export for neurofeedback, the .so5 file that you can import into the neurofeedback programs inside of NeuroGuide. If you just, for example, want to do neurofeedback on the dorsal attention network, that will both be the current density in these regions of the Brodmann areas that constitute the attention network. And you can see here which areas constitute the attention network. And you can see that Brodmann areas 7, 40, 39, and 6 on the right are significantly deviant from normal, but the other regions of the brain are not. So your protocol will involve just the deviant Z-scores, or you can adjust in NeuroGuide which level of deviation from normal you want to work with, none or all. You can also disable all, so there's none that are selected, or you can enable all. And then, of course, you can deselect any that you wish, and then create or select, and then go to export and create a neurofeedback protocol. Save that, put that protocol into the neurofeedback programs. I showed the movie already. Here are some tutorials. We're still developing these, but they have videos for the various and instructions on the various components that are inside of the Navigator, so that you can learn. And the cutting box can be used to look at the brain in different ways. For example, if I go to the volume view, you can see the slices in this manner, or you can look at it from the right. You can go from the back. And of course, if you're in the foreview, then you can navigate through these parts of the brain. I can do a coronal and a sagittal slice and go through the brain as I wish, and can add the cortex and play around with it, put the scalp back in, make the scalp not transparent, so you can evaluate the deviations from normal. That's the electrical potential. Go to data type. I can look at the Laplacian now. And in connectivity, as I showed before, you can also evaluate information flow using the phase slope index with the connectivity measures, which are the functional and effective connectivity between Brodmann areas. So this is a quick view of the NeuroNavigator as it's updated. You'll get an immediate view of what level of deviation from normal there is as you move your mouse in the lower any of these scales. And you can adjust the deviations from normal. This is information flow. And the labels change as you change the particular items that you're looking at. So this is a quick update. It's available in the demo, and of course it's available inside of NeuroGuide. And it's fun to play around, explore the brain, find out which regions are deviant from normal and how do they link to the patient's symptoms. That's the goal, is to evaluate parts of the brain that are not working right, and then target those parts of the brain for neurofeedback or for other remediation methods to identify and to help that individual with their symptoms, to reduce their symptoms. And I'm going to get rid of these sagittal and coronal sections, and you can just look at the network itself. So that's a quick view, and look forward to any feedback that people may have going forward.